let's have a look, do a quick sound check as per usual. I'm not seeing the preview. Let me try refreshing the page. Okay, now I can see it. Can I hear myself? I can hear myself. Can I see my hand moving? And that's also a yes. Okay, we're good to go. Let me go ahead and unplug this. Don't need headphones for this. Oh, I need to grab paper too. Great. Okay, now we're in business. So, I didn't really get to do much prep during this week, but I do have a goal in mind. Like I stated last week, unless somebody comes in with questions in the chat, I will just be doing some electricity and magnetism for this week and probably next week and maybe even the week after that. We'll see. My goal for today is to go over some problems that require some geometry. A lot of times students who take calculus-based electricity and magnetism will struggle with setting up the calculus because they've forgotten a lot of their geometry. So that's kind of what I'm looking for today. And we're probably going to just kind of jump around. So let me go ahead and pull up a problem from one of my physics books. Let's see. Okay, we'll start with the infinite line of charge. We will start with the infinite line of charge. And I guess this will be for an electric field problem. Okay, so electric field, at least for a point charge, electric field for a point charge is K times the charge over R squared, and then times R hat, which is just a unit vector in the direction outward from the charge. That's stuff that you should have already seen in your electromagnetism physics class. Otherwise, if you're not in that sort of class, then this session is not going to be relevant to you. But you can still watch if you want. Anyway, what do I want to do? So I want to figure out what is the electric field strength at a point that is let's call this y meters away from an infinite line of charge. And let's say that this line of charge has a uniform charge density of lambda. Let's say we've got a uniform constant charge density of lambda. Or you know what? I'll say lambda is the variable, and then it will have a value of lambda 0. All right, so how do we set this up? Well, first let's try and draw some electric field lines for point charges. You might say, well, there are no point charges here. It's a continuous line. Yes, but calculus allows us to chop it up into little pieces that are so small they can be considered point charges. So that's the way we're going to go with this. So let's say, for example, I take a really thin slice of this line between those two little dashes I just drew. Let's say we got that thin slice of charge, and let's say that that represents a point charge, and let's say that this is a positive, by the way. Okay, so electric field due to a positive point charge would just be k times the magnitude of that charge divided by its distance from the point squared. So this is going to be r. This is going to be r. And it's going to be in the direction, in the outward direction towards that point. If it's a positive charge, if it was a negative charge, it would be inward. So the direction is going to be this way. So we're going to have an electric field. I guess I'll draw it in yellow. An electric field that points that way. Except this isn't the entire story, because again, this isn't really a point charge, it's just a really small slice of a continuous line full of charge. So what I actually want to do is say that this small segment of the line contains an amount of charge that I will call dq. A small amount of charge. We'll say that the electric field due to that small amount of charge is not E, but dE, a small bit of electric field, equal to k times the amount of charges dq over r squared, and then times r hat. We'll deal with the r hat soon enough. Now, because this line of charge is infinite, for every such charge dq over here, that's a distance r from my point of interest, there should be another point charge on the exact opposite side. If this thing is infinite, then for every bit of charge that's here, there should be an equivalent amount over here. So I'm not going to be able to draw this perfectly, but let's see if I do that. So it would be roughly around here. So I could have another bit of charge over here, also equal to dq, and that would generate another electric field of the same magnitude, because it would be the same distance r away from our point of interest. So that would also be r. And it would generate an electric field pointing that way. And what we notice here is that these two electric fields have equal and opposite horizontal components. Meanwhile, their vertical components add up. They're both going to be pointing upward. So the horizontal components, we can say, are eliminated via symmetry. So in the end, if I were to look at my electric field, my total electric field is going to be pointing straight up. No horizontal components need to be considered. So rather than calculating dE, what I want to do instead is determine dEy, the y component. The x components aren't going to matter. They're going to cancel out for every single segment that I can slice this line into. If I picked a point over here and I drew an r from that point, and I drew an electric field pointing in that direction, I could find an equivalent point on the opposite side over here that would cancel out the x component with it. You could do this forever. This line is literally infinite. If it was not an infinite line, then unless this point was exactly at the middle, you'd still have to take the x components into consideration. But we've been spared from that, at least for now. So let's go ahead and see if we can come up with an expression for dEy. So we're still going to use Coulomb's constant, K. And it's still going to be based on the amount of charge dq. However, the distance is going to be different. Actually, wait. Let me think about this before I say anything stupid. Let me see. So we've got an amount of charge dq. It's going to have some distance r away from our point of interest. And I am looking for... Actually, no. No, it's still going to be the same expression. It's going to be k times dq over r squared times, for our r hat, we don't need the horizontal component of it anymore. For our r hat, we just need the vertical component of it. So let's see. The vertical component, r hat, is going to have a magnitude of 1. R hat is going to have a magnitude of 1. And its components are going to be some cosine and some sine. Let's go ahead and define the angle for r hat. So if I take a point over here, which angle do I want to use? I think I'm going to use this one. I'm going to let that be my angle theta, which would make this equal to theta, which means for the vertical component of my electric field, I would basically be just taking the sine theta component of r hat. So yeah, this would just be cosine of theta, sine of theta, just what we're used to. And the x component is not going to be relevant here for dEy. For dEy, we're just going to have times sine of theta, and it's going to be in the y direction, so I guess you can write y hat if you want to be particular about it. And I think now we can start doing some calculus. Well, we still have a little bit more geometry to go. So in order to do our calculus, we need to consider not just one particular segment of this line. We need to work with the whole entire line. So we need to come up with something that we can associate with the length of the line. And the key word there is length. I'm not satisfied with the way I worded that. Yeah, this is what happens when you don't have enough time to prepare. What's a better way to say this? Okay, so we want to take a whole bunch of these little segments that contain a charge of dq. We want to make sure that we account for all of them, going from all the way from negative infinity all the way up to positive infinity along this line. So if I'm moving along the length of the line, I guess what I want to do first is just write an integral from negative infinity to infinity with respect to length along the line. So with respect to L, and it's going to be, let's see, essentially what I'm looking for is the electric field in the y direction at position, I don't want to call it, do I want to call it L or do I want to call it X? I mean, I guess I'm just splitting hairs at this point, but I do know that some professors have a preference here, so I want to think about what I would rather show. I'll go ahead and call it X. Okay, so that's roughly what we're trying to do. We're trying to go through each and every point on an infinite line, and at each point we want to calculate the y component of the electric field that that point generates, and the integral will sum all that up. So that's the rough picture of what we're trying to look for. Okay, so this needs to be rewritten as a function of x, or L. Let's see how we want to do that. So I'm gonna have Q, which acts as a variable. I'm gonna have R, which acts as a variable here. I want to re-express both of those in terms of x or L, again, depending on personal preference, really, whether it's your personal preference or your professor's personal preference. Let me start with defining R in terms of x. So I'm going to say that this is the point where x equals 0. And then everywhere to the left of that point we're going to have negative x's. Everywhere to the right of that point we're going to have positive x's. Okay, so at some given time we're going to be a horizontal distance x away from our point of interest. How does that help me define R? Well, y is a constant, so we can now define R using Pythagorean theorem, because right here we've got ourselves a right triangle. So I'm going to say R equals the square root of x squared plus y squared, x being a variable, y being just this constant distance from the infinite line that we were given for the problem. So the only variable here now is x. Oh, and come to think of it, I forgot to square the r down there. Glad I caught that in time. Let's see. Is there anything else I need to do with this right now? Doesn't look like it yet, but we probably will have to do something with it soon. So let me go ahead and rewrite my dEy is equal to k dq over x squared plus y squared times sine of theta y hat. And come to think of it, theta is also a variable here. So yeah, we're going to also need to redefine theta. How do I want to do that? I think what I'll do is I will say, since sine of theta equals opposite over hypotenuse, I'm going to replace sine of theta with, let's see, opposite to it is the y, and the hypotenuse is r, which is the square root of x squared plus y squared. Okay, so there's another substitution we can make. So now dEy is updated to k dq over, let's see, x squared. So, well, actually, no, I'll just write the whole thing in two fractions for now, and I'll put it together on the last line. Over square root of x squared plus y squared. Notice we haven't done any calculus yet. Notice that we haven't done any calculus yet. This just goes to show how important geometry really is for an electromagnetism course. Don't sleep on your geometry. If you need to review your geometry skills, then make sure you do so. Now then, what was my next step? So dq. This is another variable that I need to redefine. I want to redefine dq in terms of dl, or better yet, in terms of dx. So what I'm going to do now is take advantage of the fact that we have a constant linear charge density. Even if your linear charge density wasn't constant, in general, charge is equal to your charge density, charge per length, times the length. Or if you have a variable density, you would say a small segment of charge is equal to your charge density would be some sort of function of L times a tiny change in L over a very small length. The charge density, even if it was not constant, over a sufficiently small length, it's approximately constant. So that's kind of the reasoning. Now then, I can say over here that L is essentially just my distance from x equals 0. So I can actually say that my L equals x, and therefore my dl can be replaced with dx. Yeah, a small change along the length of this green line is the same as a small change in x along that same line. So I can just do dq equals, for our case, we just have a constant charge density, so I'm going to substitute lambda of L with lambda 0. Of course, if you had something else, if you had something like lambda equals, I don't know, like lambda naught times L squared or something like that, then obviously that's what you would substitute in here. But since we've got just a constant linear charge density, we just sub in a constant there and we're good to go. And then my dl I'm replacing with dx, and that part is all nice and dandy. And I think with that, all of our variables have been replaced either with x's or with constants. So let's go ahead and write dEy is equal to k times lambda naught, or lambda 0, dx times y all over, let's see, x squared plus y squared times the square root of x squared plus y squared. I'm just going to write that all as x squared plus y squared to the 3 halves. This is x squared plus y squared to the 1, and that's x squared plus y squared to the 1/2. If I multiply them, 1 and 1/2 is 1 and a half, or 3 halves. So that's going to be x squared plus y squared to the 3 halves, and I just noticed it's a little too low for you to see. X squared plus y squared to the 3 halves. Is that better? A little bit. Okay, now we finally have the thing that we can integrate. The total electric field in the y direction. Speaking of which, I forgot my y hat. So the total electric field in the y direction is simply the integral from, let's see, I guess we're just integrating with respect to x, so from x equals negative infinity to x equals positive infinity of this dEy, which is just k times lambda 0 times, I'm going to write the y first, and then the dx, all over x squared plus y squared to the 3 halves. I don't even know if this thing is doable, but I guess we're about to find out. I feel like this was supposed to be rewritten in terms of theta. But we'll see. Maybe we can just do some trig substitution and be done with it. So I'm going to go ahead and grab a new sheet, and let's continue it over there. This isn't just review for you guys, this is also review for me. It's been a while since I've done calculus-based electromagnetism. Let me see, so I want to just copy down that integral. So e sub y equals integral from x equals negative infinity to x equals positive infinity of k lambda 0 y, and I forgot the y hat there, didn't I? I forgot the y hat. I mean, we know that it's in the upward direction, so I don't think it's going to be the end of the world if we leave it out of our integral. Let's see, k lambda 0 y hat dx over x squared plus y squared to the 3 halves. X squared plus y squared to the 3 halves. Okay, calculus time. So all this stuff is constant and can be pulled out of the integral. And that leaves me with dx over x squared plus y squared to the 3 halves. Remember that y squared here is a constant, so let's see what I can do in terms of trig substitution. Constant plus x squared. So if I divide both sides, or not divide, if I factor out a y squared, that leaves me with if I factor out a y squared, let's see, if I factor it out of a x squared plus y squared to the 3 halves, so that would be y squared to the 3 halves is going to be y cubed when I pull it out. then on the inside I'll have x squared over y squared plus 1. And then that's to the 3/2. Okay, that y cubed can be moved over there. It'll reduce with this y over here to a y squared. As for x squared over y squared, I'm going to go ahead and say x squared over y squared is equal to tangent squared of theta. I'm going to go ahead and say x squared over y squared is tangent squared of theta, which actually works because wait, does it? Okay, I don't want to call it theta. I don't want to call it theta. Let's call it phi. Greek letter phi. So that would be this angle right here, actually. Yeah. Okay, so x squared over y squared equals tan squared of phi. And the reason I want that substitution is because then I'd have x squared over y squared plus 1 is equal to tan squared of phi plus 1, and 1 plus tan squared of an angle is equal to secant squared of an angle. If you don't remember that trig identity, it's okay as long as you at least remember the Pythagorean identity. If you remember that sine squared of an angle plus cosine squared of an angle is equal to 1, then if I divide both sides of this by cosine squared, I get sine squared over cosine squared plus cosine squared over cosine squared, which is 1, equals 1 over cosine squared. Sine squared over cosine squared, that's tan squared, plus the 1 just gets copied over, and 1 over cosine squared, that's the definition of secant squared. So there you go. Even if you don't know all of your Pythagorean identities off the top of your head, as long as you remember the main one, you can derive all the others. And I think I just wrote over my 1 there. Okay, so now that I have that, what I'm going to do is I'm going to square root both sides. That gives me x over y equals tan of phi. And I can rewrite that as x equals y tan of phi. And now I can differentiate both sides in order to do my trig substitution. So I can do derivative of x is dx equals y is a constant, and then derivative of tan phi is secant squared. I was about to say secant tangent, but I knew that wasn't right. Derivative of tangent is secant squared, so that's going to be secant squared of phi d phi. All right, and of course x squared over y squared plus 1, we already said that's going to be secant squared. Tan squared of phi plus 1 is going to be secant squared. So let's go ahead and change colors here. Let's see. That y squared I'm going to go ahead and take out of the integral. So yeah, that y squared just comes down here. And then we've got the integral bounds may have changed, almost certainly. Let's see, my dx becomes y secant squared of phi d phi. Okay, so that takes care of my dx. And then x squared over y squared plus 1 is going to simplify to secant squared of phi, and then to the 3/2 secant squared of phi to the 3/2. And let's see if how am I defining my variables here? So phi is inverse tan of x over y, right? Phi is inverse tan of x over y. So inverse tan of negative infinity over a constant would be, let's see, that would be negative pi over 2. Negative pi over 2. And inverse tan of positive infinity over y would be positive pi over 2. So that takes care of our integration bounds. If you're not convinced by that, I would urge you to remember what the graph of tangent looks like. The graph of tangent, let me go ahead and draw my asymptotes. Okay, those are not evenly spaced. Let me draw this one closer. Okay, that's a little bit better, and scratch this one. So the graph of tan of theta, or I guess in this case tan of phi, would look something like this. So when tan of theta approaches infinity, that's at theta equals pi over 2. When tan of theta, or I guess I should say tan of phi, approaches negative infinity, that's when you're at negative pi over 2. All right, so that is taken care of. Am I forgetting anything else, or are we good to go? I think we might actually be good to go. Let's see what I can do over here. So equals, this y over here can cancel with this y over here. So no more y squared, it's just y. And then secant squared of phi to the 3/2, secant squared to the 1/2 is just secant, and then to the 3 gives us secant cubed, and then secant squared over secant cubed reduces to 1 over secant. And what's 1 over secant? It's cosine. Secant squared over secant cubed just becomes cosine. And that's from negative pi over 2 to pi over 2. And then our constants are k, lambda 0, y hat, and y. Okay, integral of cosine, moment of truth. Are we going to get an actual number, or are we going to get complete nonsense and have to go back to the drawing board because I screwed something up? Here we go. We are going to get k, lambda 0, over y hat, times integral of cosine is sine of pi over 2 minus sine of negative pi over 2. Well, I know sine of pi over 2, or sine of 90 degrees, is equal to 1. And I know sine of negative pi over 2 is equal to negative 1. So 1 minus negative 1 is 2. So we are actually getting something here. we are getting 2k lambda 0 over y. And then times y hat, which just means it's in the upward direction. Okay, so I think I'm just going to fit that right up here. Total electric field in the y direction, at least its magnitude, is equal to k times lambda 0 over y, and then times 2. Should have written the 2 first. There we go. It's kind of crowded, but you know what it's supposed to say. Okay, does this actually make sense intuitively? Let's see. So, proportional to the Coulomb constant, that's natural for electric fields. We're not surprised by that. Does it make sense that the magnitude of the electric field increases with the increase in charge density? Yes. The higher the charge density, the higher the field. Does it make sense that it decreases with distance from the infinite line of charge? Yeah, that also makes sense, because even for the simple point charge, or just common intuition would tell you that the farther away you are from a source of electric field, the less of that field you would feel. So yeah, it all checks out, as long as the only thing that you could call into question, the only thing you could cast doubt on, is the 2. If there's any mistake in this result, it would be in the 2, but all of these other quantities are definitely where they belong. What's in the numerator, it makes sense for it to be in the numerator, and what's in the denominator makes sense to be in the denominator. So I'm going to go ahead and say that I think we got it. But of course, I'm not infallible. I can make mistakes too, so if you catch something that you think I may have done wrong, then by all means, let me know. Or maybe I'll catch it myself and issue a correction, but we'll see. Time is tight. Okay, let's do another one of these. Let's do another one of these so we can keep on practicing those geometry skills. So the next one is kind of similar, except this time it's not an infinite charge distribution. I'm looking at 2 problems in my book. One is easier than the other, so I'm going to pick the harder one, of course. So it says we've got electric field coming from an arc of charge. Let's see what it says. It says a total charge Q equals 0.1 microcoulombs is distributed uniformly over a quarter circle arc of radius 9.4 centimeters as shown, and they have a graph for it. And it's asking what is the linear charge density along the arc, and then it's asking for the x component of the electric field, and then it's asking for the y component. And part D is asking how does the magnitude of the electric field at the origin for the quarter circle arc you've just calculated compare to the electric field at the origin produced by a point charge of 0.1 microcoulombs located at a distance of 9.4 centimeters from the origin along a 45-degree line. Okay, we might make that comparison. I don't know if we're going to learn that much from it, but we'll see. And then part E says do the same thing again, but for a semicircle. I think we might skip part E. Well, then again, if we do the main part of the problem, then we should be able to just we should be able to take a little shortcut. So we might do the whole thing, except I'm going to skip on the actual numbers. I'm going to skip on the actual numbers. So They have a coordinate system, and on this coordinate system they drew an arc of charge, a continuous arc of charge, a quarter circle. I think I drew that well enough. Looks to be the same distance everywhere. Well, I mean, I guess it's as close to perfect as it'll get. But that is supposed to be a quarter circle. So they said, instead of giving us a charge density, they told us it has a total charge of Q. I'm just going to call that Q0 so that we don't mistake it for a variable. And they said it has uniform density. They said that the charge is uniformly distributed over it. That means it's spread out evenly along the arc length of the arc. What else did they give us? They gave us the radius, so I'm going to call that capital R so that we don't mistake it for a variable. And that's it. So their first question is, what is the linear charge density along the arc? Their first question is, what is lambda? That shouldn't be too hard to do. If we know that it's a quarter circle, then we know how many radians this arc is. It's an arc of pi over 2 radians. This thing is pi over 2 radians. So to calculate arc length, all we have to do is say arc length S is equal to the radius times the angle in radians. So that's going to be equal to R times pi over 2. And there we go. I guess we can also write it as pi R over 2. Another way you could do this if you forgot how radians work, which is kind of a problem that needs to be addressed, but if you've forgotten how to calculate arc length from radians, then you could also just calculate the circumference of a full circle and divide it by 4 to get the arc length of a quarter circle. 2 pi r divided by 4 gives you pi r over 2. Same result. So now that we have that, we can go ahead and calculate the linear charge density. The charge per length equals the total charge over the total length. If it's uniform, it's just total charge over total length over pi r over 2. So if I just simplify a little bit, that's going to be 2q0 over pi r. All right, that's the first question they asked. Secondly, what is the x component of the electric field at the origin? And then they ask again, what's the y component? So with the line of infinite charge, we were lucky enough that the x component completely cancels out. But even if it didn't, everything we did still wouldn't have changed, because just like this problem is asking us to do, we would still want to calculate the x and y components of the electric field separately. The only difference would have been if the x components didn't cancel out here, then by the time we got this result, we would still not be done because we'd have to set up a whole nother integral to calculate e sub x. If we didn't know it was 0, then we'd have to basically do, I don't know about double the work, because a lot of it would be well, I mean, here we would have had to do no work because, again, it's 0. But I'm trying to think of a case where, like the current case, even with the current case with this arc of charge, we're going to see it's not really double the work because there's a lot of similarity between how we calculate the x component and how we calculate the y component. So it's not necessarily the case that our work doubles. We'll say roughly you would do 1.5 times the work on average. Sometimes more, sometimes less. But that's enough of me rambling. So they said find Ex. Find the magnitude of the x component of the electric field. And at what point was it? At the origin. So our point of interest is right here. A distance of big R from our arc of charge. Okay, I think I want to actually just pick a random section of this arc, let's say here. It's going to contain a charge of dq, which will act as a point charge, and it will produce an electric field that points in that direction. Let me switch colors here. So it'll produce an electric field pointing that way. I'll call it DE, since it's just a portion of the total electric field. And I think, did I draw that right? It's slightly off, but we'll assume that that's a straight line. Okay, and we want the x component of that. So for the x component, if I define this angle to be theta, then that's the same angle as this right here. And for DEX, every single x component I'm going to have, whether it's this point that I picked for my DQ or any other point along the arc, you can see that if it has an x component at all for the electric field that it produces, the x component is going to be to the left. So for the direction, it looks like we're going to have the negative x hat for our direction, or negative I hat, I suppose, if that's what you prefer. Anyway, k times dq over r squared. This time r is going to be just big R, regardless of which dq you pick along this arc. So big R squared, that's constant. K dq over r squared. R hat, our r hat this time is going to be negative x hat. Or, again, negative I hat if you prefer. And come to think of it, back in this problem when I was saying y hat, we could have also called it j hat if that's more familiar to you. Okay, so I want to... what do I want to do next? I guess I want to define dq, because that's... well, I mean, I can't really integrate this. If I integrate both sides of this, then integral of dex is just going to be e sub x, the total x component of the electric field. So we don't need to worry about the integration bounds there. But what about this? The integration bounds for if q is my variable, where does q start and where does q end? It doesn't really make sense. So we're going to need to change variables here. We can't keep q as our variable. We need something else. And that something else is going to be our theta this time. Theta is a nice variable to use because we can have it start at 0 for this little slice and then work our way up to pi over 2. That would give us nice integration bounds. And so let's see if we can express dq in terms of theta. Let me erase that. I don't even know why I wrote it in the first place. Let's see. So dq, can I write it in terms of theta? Well, first of all, dq in terms of our charge density is equal to the charge density times whatever change in length contains that amount of charge dq. So it's going to be a small segment of the arc length, and we already know that arc length is equal to radius times theta, so I can say since s is equal to r times theta, r being a constant, theta being a variable here, then ds is equal to big R times d theta. A small segment of arc length is equal to the radius times a small change in theta. Okay, so with that we can do dq is equal to lambda times ds is now r times d theta. And we already solved for lambda earlier. Lambda is 2q0 over pi r. So we can say dq is equal to 2q0 over pi r times the r we copy over, and we copy over the d theta as well. The r's cancel out. And yeah, we just have a bunch of constants, interestingly enough. I think this one might actually be easier than the previous one in terms of how it integrates. So theta is a variable that we can work with because, again, we can write very clear integration bounds for it. It just goes from theta equals 0 all the way up to theta equals pi over 2. So let's go ahead and do that. And I think we'll be able to copy most of this work over for the y component. Let's see. So dEx, equals the integral from 0 to pi over 2 of k times all this stuff, 2q0 over pi times negative x hat d theta all over big R squared. Did I do all my substitutions correctly? K copied over, dq substituted with all that stuff, copied over the negative x hat, and copied over the big R squared. Yep, we're good to go. Okay, so all of this stuff is actually constant, and we can pull it out of the integral. Like I said, this is going to be a really easy integral. It's just the integral of d theta. It's just the integral of d theta from 0 to pi over 2. Integral of d theta is theta, and then plug in pi over 2 minus plug in 0. Pi over 2 minus 0 is pi over 2. So yeah, we're just 2q0 over pi all over r squared times negative x hat times integral of d theta is theta from 0 to pi over 2. And yeah, that's just multiplying by pi over 2. This pi cancels with this, and the 2's cancel out as well. And that leaves us with k q0 over r squared and times negative x hat. I know it kind of spilled over into this section, but interesting. So this is the same electric field we would have gotten from a point charge. This is the same electric field we would have gotten from a point charge that was placed right here. If I placed a point charge right over there, and it had a magnitude of q0, then I would have gotten the exact same electric field as this arc is giving me. I think that has to do with the question that they're asking for part D, or maybe it was E. Speaking of other parts, the next part is asking for the y component of the electric field, and for the y component we go through a very similar process. I don't think you need me to reiterate what I've already said for the x component. If we pick some random super small section of this charged arc containing a charge dq, then it'll create a small segment of the total electric field, a small portion of it, and this time, instead of the cosine component, oh, wait a minute, actually, come to think of it, I forgot to write the cosine, didn't I? I did. I knew something was up. Yeah, because this was surprising me because it felt like it was too much, considering that there's a total charge of q0 spread out across this whole arc. It didn't really make sense for it to have an x component equivalent to having all that charge just concentrated here. I knew something was off about that. Okay, times cosine of theta. But then that means my integral changes. If I'm integrating cosine theta d theta, that's sine of theta. So instead of pi over 2 minus 0, it should actually be sine of pi over 2 minus sine of 0, which is 1 minus 0, which is 1. So then the pi over 2 isn't there, which means the 2 and that pi don't cancel. That 2 and that pi do not cancel. Is there anything else that needs to be changed? No, I don't think so. So rewrite that 2, rewrite that pi, and over here we'd still have 2 and then over pi. Okay, I think that fixes it. Am I missing anything else? Let me double check. I don't think so, but let's just rewrite it for the sake of clarity. E sub x is equal to 2k q0 over pi big R squared times negative x hat. All right, now for the y component. So as I was saying, if we pick a small sliver of this arc that contains a small bit of charge dq, it'll produce an electric field at the origin of magnitude dE. And for its y component, dEy would just be dE times sine of theta. So Ey is equal to the integral of dEy, and dEy is equal to Ey times sine of theta. At least the magnitude of dEy is equal to the magnitude of Ey times sine of theta. Everything else, I'm pretty sure, just works out the same, right? Because yeah, that's really the only difference. The stuff in the integral stays the same. dEy is just going to be pretty much this right here. Integral of k dq over big R squared times sine of theta. This time I'm not forgetting it. And then for the direction, it will be for every single segment along this arc, the y component of dE is always going to be pointing downward in the negative y direction. So I'm going to say negative y hat, or if you prefer, negative j hat. Okay. And we already know what this turns into. This just turns into all of that. Well, it's better to say it turns into all of this. So the dq gets replaced with 2q0 over pi d theta. Let me go ahead and continue this on another sheet. Q0 over pi and sine of theta and d theta. Sine of theta and d theta. Okay. Oh, and I forgot. Times negative y hat. All right. we can pull all those constants out. Let me switch colors. So that leaves us with 2k q0 over pi big R squared, and then times negative y hat, and integral from theta equals 0 to theta equals pi over 2 of sine of theta d theta. The integral of sine theta is negative cosine of theta. A lot of people forget the negative. Let's make sure we don't add to that statistic. Integral of sine theta is negative cosine theta, so I'm getting 2k q0 over pi big R squared negative y hat times negative cosine of pi over 2 minus negative cosine of 0. Cosine of pi over 2 is 0. Minus negative, that's a plus. And then cosine of 0 is 1. So times 1. Not a surprise here. 2k q0 over pi r squared negative y hat. Not a surprise that it has the same magnitude as the x component. And come to think of it, I forgot to write the integral symbol there. I think someone is calling me. Hold on. Let me mute the mic. All right, I am back. That was quite the long phone call. I'm definitely going to have to edit this part out when I upload the video, but if you don't pick up those calls as soon as they come in, you miss out on a student. Would be nice if people would give me a break on my day off, but that's the nature of being self-employed, ladies and gentlemen. It's a good hustle. Anyway, what were we doing? So we just finished getting the y component of our electric field. Let me see. What else did they ask for us? So part D says, how does the magnitude of the electric field at the origin for the quarter circle compare to the electric field at the origin produced by a point charge with the same Q located the same distance along a 45-degree line as shown in the figure? Okay, so basically, if we go back to the original drawing, they're saying if instead of this arc, if we took all that charge and we condensed it into a single point right here at a 45-degree angle, how would that compare? How would that compare? So for a point charge at that position, I'm going to go ahead and just draw it. If I put a point charge of q0, a distance r away from the origin at a 45-degree angle, what kind of electric field does it produce, and how does it compare to the one we just calculated? Well, let's see. So I don't think it's going to be the same. I think I can already see that it won't be. So the total magnitude of this electric field would be k q0 over r squared at that 45-degree angle. So I guess your r hat would be negative root 2 over 2 comma negative root 2 over 2. And that's definitely not what we have for the x and y components of the electric field due to the arc. The electric field due to the arc, instead of root 2 over 2, we've got 2 over pi. Yeah, 2 over pi. Not root 2 over 2. So I think it's immediately apparent that they're not the same. Let's see. How do they differ? Like by what factor? If I compare 2 over pi divided by root 2 over 2, that becomes 4 over root 2 times pi. 4 over root 2 and also over pi, 0.9. I'm getting 0.9003 and then a bunch of other weird decimals. So it looks like the arc of charge overall produces a weaker electric field, is what I'm seeing. I'm seeing a weaker electric field overall from the arc of charge compared to just a point charge. All right, good, good, good. And then we have, let's see. Part E is asking, what's the magnitude of the electric field at the origin produced by a semicircular arc of charge 2 times the original charge? Okay, so now they're saying, for this next part, I'm not even sure I want to do it, but they're asking, what's the magnitude? Oh, actually, we can do this one really easily. So this time, instead of a quarter circle, they've got a semicircle. They've got that. And then the total charge on this thing is 2q0, and again, it's distributed uniformly. So what is the total electric field here? Well, we already know, because we can just treat this as 2 arcs. Arc 1, which we already did before, arc 1, which is going to be this, is going to have an electric field component pointing to the left and an electric field component pointing down. And the other arc is going to have an electric field pointing to the right and another one pointing down. Left and right are going to be equal and opposite. They're going to cancel out. So all that we're left with is the downward components, which were the EYs. So this one is really easy. EY of this semicircle is going to be 2 times EY of a single quarter circle. So it's going to be, instead of 2, it's going to be 4k q0 over pi big R squared in the negative y direction. Done. All right, at least that last one was easy enough. And that one deals with point charges. We don't need to mess with that. Where do I want to go from here? I guess we'll do some Gauss's law next, because That's the next area of geometry heavy stuff. All right, let's have a look at what we've got. I want to pick a good one first. Again, I want something that really emphasizes the geometry. I might just modify one of these and create my own problem based off of it. What does this one say? Point charge in a charged sphere. A point charge is located at the center of it. Oh, that's a conducting shell. You know what? Why not? It says we've got a point charge. I'll just call it negative Q, located at the center of a thick conducting spherical shell with inner radius A and outer radius B. The conducting shell has a net charge of Q2. I'm just going to call it positive Q. Actually, you know what? I'll keep the 1 and 2. So for the point charge, I'm going to call it Q1. For the total charge on the conductor, I'm going to call it Q2. And it says, what is the magnitude of the electric field at a point located a distance of 8.8 centimeters. I'm not going to worry about the actual numbers. I'm just going to call it a distance r. Any other good questions here? It is asking for the surface charge density on the outer and inner parts of the shell. Those are good questions. And I think that's that. Okay. Let's go ahead and get out a new sheet. Let me see here. So I'm not really good at drawing these things. I imagine most people are not, but I'll try my hand at it. So we have, I'm going to draw an open sphere, or at least my best attempt at one. Yeah, that doesn't look right. What am I doing wrong? What am I doing wrong when I draw these things? Okay, I think I know what I did wrong. Let's try that again. So, sharper arc there. Something more circular there. And then something like this. Okay, that looks decent enough. So we have a point charge here in the middle. it's a charge of Q1. Q1. We have an inner radius of A and an outer radius of B, and this is a conducting spherical shell. Conducting spherical shell. So essentially what I've done is I'm showing you like a slice of it. Maybe it would help if I drew a faint line there. Yeah, and then... Oh, I did not draw this too well, did I? Yeah, the center is a little bit off. Something like that. Yeah, I guess it'll have to do. As long as you know what it is that we're trying to represent here. So I've got a sphere, and I've basically opened up a piece of it so that we can see what's inside of it. Actually, let me just show you the drawing in the book. That's what I'm trying to draw right there. I don't know why I didn't think to do that from the beginning, but yeah, that's what we're looking at. Okay, so we were told that the conducting shell has a total charge of Q2 on it. Q2 is the total charge on this conducting shell, but we don't know how that charge is distributed. You can't assume it all lies on the outer surface, nor can you assume it all lies on the inner surface. In fact, it probably is split between the inner surface and the outer surface, and probably not evenly. That is quite the phrase, probably not evenly. That sounds like, I don't even know, it just sounds like a really gibberish phrase. But anyway, we were asked to, what were the interesting questions again? Well, for the electric field, what I always ask when practicing Gauss's law, you should really just practice identifying what the electric field is in every, what I like to call, region of interest. So magnitude of the electric field as a function of r, which is just distance from the center in this case, is equal to, it's going to be a piecewise function. And how many pieces does it have? So our first region of interest is from the center until you reach the inner surface of the shell. So that's going to be r from 0 to a. I doubt this is enough room to actually write what the function is going to look like, but we'll see. And our second region of interest is from A to B, so r from A to B. And our third region of interest is anything outside of the shell, so any place where r is greater than b. And actually, I guess I can say, I'll say or equal to over there and greater than or equal to here. I wouldn't split hairs over that, whether you should use greater than versus greater than or equal to, less than versus less than or equal to. I wouldn't worry about that too much. No need to split hairs over it. If your professor is very particular about it, then just follow what your professor says, but otherwise, don't worry about it too much. Anyway, those are our regions of interest, so I'm just going to go ahead and apply Gauss's law in each of those regions of interest. So first region of interest is I'm going to imagine a Gaussian sphere of radius greater than 0 but less than a. So somewhere inside here, a sphere that envelops this point charge and nothing else. What would the electric field be on the surface of that sphere if the radius of that sphere is r, which again is a value between 0 and a? Well, Gauss's law tells us that the flux is equal to integral E dot dA is equal to the charge enclosed over epsilon naught, or epsilon 0 if that's what you prefer to call it. As for the integral of E dot dA, because of symmetry, we can simplify this to just E times the surface area of our Gaussian surface. We know because of symmetry that the electric field is going to be the same value at every point on our Gaussian sphere. Maybe I should draw it. Okay. I don't want to draw it over this because then it's going to be a mess. So what I'll do instead is I will draw this. Let this be a sphere surrounding our charge Q1, which I'm just going to draw right here in the center. So we know that the electric field is going to be the same at every point from this sphere. Q1 was a negative charge, so I should be drawing those arrows pointing inward, not outward. My mistake. But regardless of whether it's inward or outward, the electric field at each point on the surface of this sphere is going to be the same because each point on the surface of the sphere is an equal distance away from the point charge, and we know that the electric field of a point charge is equal to k times the magnitude of the charge divided by the distance squared. The distance is the only thing that could be variable here, and we know that the distance is the same for each of these points. So yeah, same electric field for each and every point on the surface of the sphere. I'm sure you didn't need me to reiterate that, but just in case you needed a refresher, there you go. So we know the electric field is the same at every point, and we also know that the direction of the electric field with respect to the direction of the surface normal, that would be the direction of dA, always normal, perpendicular to the to each section of the surface. Well, the surface normals always just point directly outward from the surface. So the dot product becomes a simple multiplication, and since the electric field is inward while the surface normals are outward, you'd just get a 180-degree angle, so the dot product becomes a multiplication with a negative sign. So effectively we get, well, actually you don't even need to include the negative sign because you're already going to get it when you substitute in for E. When you write the Q value in for E, you're going to substitute a negative value in there anyway, so you'll be getting your negative sign from that. So again, no need to worry. Okay, so I'm just going to say E times integral of dA is just A, so this is a surface of the sphere equals Q enclosed over epsilon naught. So if you've done Gauss's law enough times, then you notice that the integral part always simplifies to E times A, because in this level of electricity and magnetism, you deal with really simple geometries, really simple symmetries. that always reduce to a simple multiplication. So you don't usually have to do any actual calculus on this side of the equation. The real difficulty is determining Q enclosed for a lot of students. This problem isn't going to be too much, but I can spice it up by making this an insulating shell, which I think I will do in a minute. For now, the charge enclosed in our first Gaussian surface of radius between 0 and a is just Q1. So we get equals Q1 over epsilon naught, and then for E times a surface, the surface area of our sphere is 4 pi r squared. A lot of students forget that the surface area of a sphere is 4 pi r squared. Let's not be among those students. I could tell you stories about my classmates in physics being called out by my college professors for not knowing volume and surface area of a sphere. It's something you learn sometimes as early as like 4th or 5th grade. It's not something we should be forgetting. Anyway, solving for the electric field, divide by 4 pi r squared, and we get magnitude of the electric field equals Q1 over 4 pi r squared epsilon naught. This is the same as k Q1 over r squared, because 1 over 4 pi and epsilon naught is equal to k. You can try it out on your calculator if you don't believe me. You can look up the value for k and look up the value for epsilon naught and see that 1 over 4 pi epsilon naught is equal to k. Anyway, so I'm just going to go ahead and write it as Q1 over 4 pi epsilon naught times 1 over r squared. And I don't need to add the negative sign because that will be added in once you substitute the value of Q1 as whatever they said, -9 microcoulombs. I'm not going to worry about numbers like I said before. Now then, we take a look at our next region of interest. Our next region of interest is between the inner and outer surface of the conducting shell. This one should actually be really easy. This one is 0. How do we know? Because for conductors, any time you look at the electric field in a conductor, if it's inside the body of the conductor, if it's inside the bulk of the conductor, it must be 0. Electric field can only exist on the outer surface or inner surface. Actually, wait, no, hold on. Electric field can only exist before you reach the inner surface of a conductor or once you head outside of the conductor, but never when you're within the bulk of the conductor. Well, with an asterisk, because there is a way to make it happen. But I'll go over the logic a little bit. So suppose you have a conductor and I exert some sort of electric field on it. Let's say I have a machine that generates an electric field like so. So this is an external electric field. What does this electric field do to a conductor? Well, with a conductor, the electrons are free to move around. So if they get pushed by an electric field, or I guess pulled, then again, they're free to move, so they will. So I'm going to have positive and negative charge together at first. Then they get subjected to an electric field. These negative charges will move against the field. Positive charges stay in place because protons are in the nucleus of the atom. They aren't free to move around without moving the whole atom. So the electrons move closer to the source of this electric field. And then what happens is, sometime later, so that was before, and after, the positive charges that were down here are left behind, and now the negative charges have come over here. Well, positive charges produce an electric field pointing away, while negative charges produce an electric field pointing towards them. So what's going to happen is you're going to generate a counter electric field. I'll call this the internal electric field. And if this internal electric field is weaker than the external electric field, what's going to happen? The same thing that's been happening. This external electric field will continue pulling electrons towards it while leaving protons behind. But the more and more that happens as time progresses, and more negative charge builds up here, leaving behind more positive charge built up here, this internal electric field gets stronger. Eventually, it gets so strong that it cancels out with the external electric field. And that leaves you with a total electric field of 0. Now, there is a scenario where this might not happen. And that's if this external electric field is so strong that there aren't enough electrons inside this conductor to produce a high enough internal electric field to cancel out with it. After all, electrons don't just materialize out of thin air. We have a limited quantity of them. Even if it's billions and billions and billions of them, a billion 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 is still a finite number. So it is possible to have a non-zero electric field in the bulk of a conductor, but it's going to require a super strong electric field. How strong? I haven't done the math. I guess we could do that. You know what? I might actually make a separate video for that, because now I'm curious. Watch me forget about it in like 2 days. But we could do a calculation based on, like, we could take the material of the conductor, let's say it's a conductor made of copper, for example, and bring out your periodic table and count the number of free electrons in copper and determine things like how many copper atoms would be in a ball of copper of a particular size, and figure out what is the maximum electric field that could be generated if you took all of the negative charge and just stuck it into one small point within that conductor. How much of an electric field could we get theoretically? I imagine that calculation would be a bit difficult if we don't make a couple of bold assumptions, but if we did make those bold assumptions, I guess we'd be overestimating the electric field, which would be okay if the question is just finding an external electric field. Okay, I'm overthinking this. Let's continue with the problem. So, already took care of that. Electric field within the bulk of the conductor is 0. But there's more to it than this. If the electric field is 0, then by Gauss's law, the charge enclosed must be 0. If the electric field is 0, then 0 times the surface area, surface, not surface, 0 times the surface area equals charge enclosed over epsilon naught. We know epsilon naught isn't 0, and we know, actually it doesn't matter what the surface area is this time, so the Q enclosed must be 0. So how much charge is enclosed if I were to draw my Gaussian surface, if I were to draw a Gaussian sphere that envelops all of that? Well, it would enclose Q1, but it can't only be Q1 because Q1 is not 0. So there must be some other charge equal to negative Q1 somewhere in here. Where is it? It's going to be gathered on the inner surface. It's going to be gathered right here on the inner surface of the conductor. So there's a total charge of negative Q1 over there. Q enclosed equals Q at, I guess I'm going to call it QA since it's at a distance of A from the center, plus Q1. This leads us to the conclusion QA is equal to negative Q1. All right. And that takes care of that. We're going to need this result in a minute. Next up, I want to do a Gaussian sphere of radius greater than b. So basically, I want to draw a sphere that encloses this entire setup, this entire system. Okay, same deal as before. We apply Gauss's law. Maybe I can fit it into this little corner here. Let me switch colors. So, because of spherical symmetry, we know whatever the electric field is, it's going to be the same everywhere. So constant times the surface area of that sphere is 4 pi r squared. This time r is greater than or equal to b, not the same as this r, which is between 0 and a, equals charge enclosed over epsilon naught. We can divide by 4 pi r squared and get the same denominator we got over here. So let me actually go ahead and write that down. 4 pi epsilon naught times 1 over r squared. That part is all the same. What's different is the charge enclosed. How much charge do I have inside here? I've got the point charge, and I've got the charge on the inner surface, and now I also have the charge on the outer surface. I don't know what the charge on the inner surface and outer surface are individually, at least not yet, but I do know that the total charge on the conductor part of it, so QA plus QB, is equal to what they called Q2. Well, yeah, they called it Q2 and I called it Q2 as well. It's just they assigned a number to it while I'm not bothering with the number. So charge enclosed is going to be Q1 plus Q2. Q enclosed, I guess I'll do it up here. Q enclosed is equal to Q1 plus Q2. And I'll go ahead and write it here, Q1 plus Q2. Q1 being negative, Q2 being positive, at least the way they described the problem. And if you substitute in the numbers, you can figure out which one wins over in the end. Which one was it? Q1 was negative 9, Q2 was 2.3. So overall, Q1 plus Q2 is going to be negative. Anyway, there was a part here that was of interest to me, which was, yes, what is sigma B and sigma A, the surface charge densities on the inner and outer surface of this conducting shell. And I think I can still squeeze that onto this page without having to start a new page. So I'm going to go ahead and do that. Let's see. Sigma A is going to be, well, on a conducting surface, as long as you don't have any sort of weird asymmetries, then the surface charge density is going to be uniform. So it's just going to be the total charge QA on the inner surface divided by the total area and similar reasoning applies to the surface charge density at a distance b on the outer surface. Sigma b is going to be QB over the surface area at distance b from the center. Okay, well, what is QA? We determined earlier that QA is equal to negative Q1. So we can substitute negative Q1 into there. What about the area? The area at a distance of a from the center is just the area of a sphere. A spherical shell really is just a big sphere minus a smaller sphere that was carved out of its center. So you can think of the inner surface area of a spherical shell as the outer surface area of whatever smaller sphere got hollowed out of it, got carved out of it. So that would just be 4 pi r squared, with r this time being equal to a. So the inner surface area is just 4 pi a squared. So this is equal to 4 pi a squared. And that's how you get sigma A. What about sigma B? So similar reasoning for calculating the surface area. It's going to be 4 pi b squared. But what about QB? That we have not calculated yet. But we do know something. We know that the total charge on the conducting shell is Q2. And the total charge on the conducting shell equals the total charge on its inner surface, QA, plus the total charge on its outer surface, QB. So QB is simply Q2 minus QA. If we subtract QA on both sides, QB is Q2 minus QA. And QA is negative Q1. So Q2 minus negative Q1 is Q2 plus Q1. Q2 plus Q1, which is actually still a subtraction because Q1 is negative. Gotta be very, very careful with your signs here. Make sure everything you're adding or subtracting still makes sense. Part of the problem is that another student could just as easily write this as Q2 minus Q1 and still be right if they define Q1 as the magnitude without the actual sign of the charge. So something to be very careful about. Whatever convention you adopt, whether you just copy everything down as magnitudes and remember the directions and signs separately, or whether you include the signs in the values of the variables themselves, whatever your preference is, once you make a choice at the beginning of the problem, you stick with that choice throughout the whole problem in order to avoid any inconsistencies. Is there anything else that I can do with this problem? They do have a question here. It says, for how many values of x, I'm going to say how many values of r, is it true that the electric field is 0, none, 1, or more than 1? At how many points is the electric field 0? Well, we know it's 0 everywhere from A to B, but are there any other points where that happens? Well, this can never be 0. And this over here can also never be 0, because whatever q1 plus q2 is, it's not 0. q1 does not equal negative q2, that's for sure. So yeah, I guess it's just between A and B. Okay, that was not as exciting as I thought it would be. And I don't see anything else here that would be of interest. Well, I would like to go on, but it is getting late, and I know I started late, and on top of that, I had to cut things short a little bit because of, well, not cut things short, but we had to skip a good 10 to 20 minutes because I had to take a phone call. But I think I'm just going to wrap things up here for tonight, and we'll just resume this next time, I hope. Maybe I'll upload a couple of videos to the channel if I find the time for that throughout the week. But otherwise, I'm afraid you guys will have to wait until next week for us to do some more. We're going to continue with Gauss's law. I'm probably going to do like an insulating shell version of this so that we can continue practicing that geometry stuff, because it really is important. And yeah, I think that'll be that. Is there anything else I want to say before I wrap things up here? Oh, right. So I've been thinking about it, and I feel the need to delay these office hours a little bit more. So I'm thinking of pushing back the start time by half an hour. We'll try that first, and if that doesn't work, then I'm going to try pushing it back a full hour. So starting next week, office hours will be half an hour later than what we've been doing for the past couple weeks. And if that doesn't work out, I'll push it back another half hour. So we'll see how it goes, but I'll make sure to edit the schedule on Twitch, and yeah, I think that's all my announcements. So take care, study hard, and I'll see you guys next week.